Hi, my name is Andy Ponce, and I am a master's student here at Fresno State. And the title of my research project is Analysis of Marked Spatial Point Patterns with Composition Valued Marks. And I know that's kind of a mouthful, but we'll go through it and break it down. And so a quick outline of what I'm going to talk about is I'm first going to tell you some background information about point patterns and point processes. And then I'll tell you about the purpose of my research project. I'll take you through the methods that we've done so far, and then we'll talk about some conclusions and the further direction, future direction that we plan on taking. And so let's start with some definitions. So the first one you'll see is for the spatial point pattern. And so a point pattern is just an arrangement of any data points in three-dimensional or two-dimensional space. And we usually call these data points events. And so the example that I like to think about is like the locations of earthquakes and their aftershocks. And so the data that's more, in a way, valuable is the locations that they're happening, because we care about where these earthquakes are occurring. And so the second definition is for the point pattern process. And this is like the underlying process that is behind the point patterns. And we call these processes stochastic because they're random and they're a little bit tricky to approximate. An analogy that my advisor likes to use that I like, I feel like it helps me understand, is think of the process as this robot that you can't see, but you know that this robot is deciding where to plot the points. You don't know how the robot is deciding or the actual process it's using, but you know that it plots the points. And so these points generate point patterns because they're in space. And these have properties. So if you look at this bottom left image, you see that the points are kind of spread apart and they're not overlapping. And so this is a point pattern with a lot of regularity or repulsion. In this middle image, you'll see that the points, you have a little bit of both. You have points that are further apart and some that are more together and kind of touching. And so this point pattern is expressing more like spatial randomness. And at the far right, you have points that are a lot more clustered together. And as a matter of fact, some of the points are very dark, which implies that you have overlap of points. And so this point pattern is expressing a lot of clustering or attraction. And so the work that we've done up until this point, we've done using the R language through RStudio. And we've applied our work to a Seabirds data set. And this set has about 127,000 rows of data and about 500 variables or 500 columns. And so the main chunk of this data is that it's made up of the recorded locations and counts of nearly 500 different seabird species in the North American East Coast and Atlantic. And so we talked about point patterns a second ago, but I didn't mention something that I'm going to talk about now, which is the marked point pattern. And so just like the other point patterns, we have the points in space creating this pattern. But these points have additional data that we call marks, and these marks are attached to each point. And so if you think back to the earthquake example, you can think of a mark as the magnitude of an earthquake. So not only do we know the location where the earthquake happened, we also know the mark of it, which is the magnitude. And to kind of give you like a visual expression of what this looks like, unmarked versus marked, we generated some plots from the Seabirds data. And what we did here is we took all of the seabird points, the data points that have at least one bird recorded of the northern gannet species. So any points that didn't have any northern gannet species were taken out. And now that we have these points, we plotted them. And you might kind of see that these points almost make an outline of part of the East Coast in the US. And you'll notice some clustering in some areas. In some areas, you have points that are by themselves. And that's kind of all we have. The points themselves aren't very different. They're all about the same size. However, if we take into account the amount of northern gannet birds at each location, the plot looks a little bit different. And so here you're actually looking at the same plot of points, but it looks a little bit different. And that's because the circles are now different sizes, if you pay attention. So some of the larger circles are telling you what this legend over here is expressing. And so larger circles are representing higher counts of northern gannet birds. And these smaller circles are representing a smaller count. So just like the earthquake analogy or example, sorry, not only do we know where northern gannets were spotted, but we know how many were spotted right there. And so now let's talk about the different types of marks. So marks can be real valued, which means they can be any number, usually positive, but any number between 0 and infinity. We can also have marks that are categorical, and you can think of these as more like labels. So going back to our earthquake example, you might think of a categorical mark as maybe the label of like whether the earthquake was deadly or not deadly, categorizing them that way. And numerical marks, going back to numbers again, those marks can either be discrete or continuous. Discrete, an example of that is the count of birds, and they're discrete because they're whole numbers. So you have either 1 bird, 2 bird, 3 birds, or so on. An example of a continuous mark is what we did in our work is we took marks as proportion of birds relative to total number of birds. And I'll explain this a little bit more, but just know that this proportion is a decimal between 0 and 1. It's not a whole number. And so let's keep going. So the purpose of my research project is to establish a framework that better fits compositional valued marks. So a second ago, we talked about marks that are categorical and numerical, but the issue here is that compositional valued marks, there isn't a lot of work done with that yet. And so that's what we're trying to help establish. And a couple of objectives that we have to take care of along the way is the first one we have to do is we have to extend existing definitions about mark statistics or just ways of measuring statistically point patterns and processes. And the main ones that we focus on are what we call the mark variogram and the mark correlation function. And we have to rewrite these in a way where they better fit compositional valued marks because they don't really fit them that well the way they are right now. We also need to apply this to the seabirds data set in order to describe codependencies and interrelationships between the species of birds. We want to know how they're interacting. What are the ecological pressures between them? And so the methods that we took are the following. The first thing we did is we took a trivial or a more simple case of the seabirds data set. We created a point process that only has one count of seabirds as the mark. So there's only one mark. And remember, this count is a discrete number and it has to be greater than 0. So 1 bird, 2 bird, or 3 birds, or so on. The second thing that we did is we generated another point process, but this process has 2 marks. And this process these marks are with respect to 2 different seabird species. And so what we did first is you'll notice here we have northern gannets and we have great shearwater. So what we did is we took the seabirds data again, and we took all of the points that have at least one of the northern gannet and one of the great shearwater. And from these points, we created marks. So mark 1, we took the number of northern gannet birds at one specific place, and we divided by the total number of birds, which is the number of northern gannet plus the number of great shearwater. And so this fraction gives us a percentage of northern gannet at any point. Mark 2 is kind of the opposite. It's the percentage of great shearwater. And these marks are between 0 and 1. They're decimals. We use the mark correlation function because it helps consider correlation between marks of any 2 points within a distance r, and it compares this to the independent case. And the last thing we did is we used the mark variogram to measure how similar the marks of 2 points are. And so now let's look at some results. So you'll see here that we have a mark correlation function plot, And this is for that first process that we generated, the one with just one mark as the northern gannet counts. And so the mark correlation is telling us how correlated two marks are depending on the distance between the points. And anything that's really close to 1 up here is expressing a weaker correlation. And so knowing that, we see that there's a strong correlation around 200 kilometers. So points that are 200 kilometers apart have a stronger correlation. It's not very short. It's not very obvious yet what that correlation is, but we know around what distance it's happening at. And now for the process with the two marks, the two proportional marks, the plots look a little bit different. And so this P noga is with respect to the northern gannets, the proportion of that bird. And we notice that at first this is kind of going down, a downward trend. And for the great shearwater, it's the opposite. It's going up first and then kind of coming back down. And so even though these are plotted separately, we kind of see a little bit of a relationship. And so we see that this drop right here is almost expressing like a small proportion of northern gannets wherever there's a high proportion of great shearwater, and so on. So they're kind of conversely related. Now let's talk about the mark variogram. And so here we're looking at how close, how similar two marks are. So remember, our marks are numbers here. So the closer the numbers, the smaller this value over here, because the mark variogram actually subtracts these numbers within its equation. And so the closer those numbers are, the smaller the difference, the smaller the point on the graph. And so we see that beyond a distance of 0 kilometers, the marks of points are pretty similar when points are about a little bit over 200 kilometers apart. And this is for the case of the first process with 1 mark. And now looking at the next process again with the 2 marks, we see that it's a little bit different. And so for the proportion of northern gannets, the proportions are very similar at about a little bit below 150 kilometers apart. And for the great shearwater, we kind of have the same case. At about 150 kilometers, the proportions are very close. And so those are the results that we have so far. And so now for the future direction. So the next thing we have to do is we have to construct a point process with more than just 2 species. Remember, we have about 500 species in the data set, and we want to take advantage of that. But also, you notice that the plots for the 2 birds, the plots were separate. And that's because the marks are still being handled separately. But we want to figure out a way to do the marks so that the compositions are all together in 1 mark. And we also need to rewrite the correlation function and the mark variogram functions, as mentioned earlier, so that they better fit compositional valued marks. Lastly, I'd like to thank my advisor, Dr. Ervin Valderrama, for all his support and guidance.